Hi, in this video we talk about analytic geometry. We will cover not only Euclidean but also curved spaces as well, but primarily we will focus on Euclidean geometry. So what is analytic geometry? We have seen the axiomatic structure of geometries, which means that we provide a set of axioms that are talking of the properties of points and lines. However, we want to do computer graphics, so we want to get the computer to work with geometry. And the computer is never able to deal with abstract terms like axioms, points, lines, intersection, etc. A computer can deal with numbers, so these concepts should be translated to numbers or computations. Generally speaking, to an algebra, which is just a collection of numbers, operations, equations, functions, etc. If the geometric concepts are available in some algebraic form, then it's pretty easy to translate it further to a, say, C++ implementation. So we have to find a correspondence between geometric concepts and an algebra. This correspondence should reflect the axioms. Having established this correspondence, we can forget the axioms because the correspondence itself encodes the knowledge of the axioms. And from this point, we can deal with only numbers, operations, equations as required by the computer. So this is analytic geometry, doing geometry with numbers. The possibility of expressing geometric concepts with numbers is provided by the coordinate systems. Here, we are going to take an external view, which means that our geometry is embedded in a higher dimensional space. So, for example, when we talk of two-dimensional planar geometry, this two-dimensional plane is included in a three-dimensional space, and when we discuss three-dimensional geometry, the geometry is embedded in a four-dimensional ambient space. The advantage of this extra dimension is that we can discuss not only Euclidean but also non-Euclidean geometries as well. Of course, it would be rather challenging to depict four-dimensional spaces on PowerPoint slides. Therefore, in figures, I always describe the situation when we embed the two-dimensional plane in a three-dimensional ambient space. So this is our ambient space. When we deal with two-dimensional geometry, the ambient space is three-dimensional, and we have an extra coordinate in addition to the xy Cartesian coordinates, and this extra coordinate is w. I use w instead of z because in three-dimensional geometry we will have the Cartesian coordinates x, y, z, and w is added as an extra dimension. So a point in this ambient world is described by three numbers, x, y, and w. And for such points or triplets, we assume the operations of addition when coordinates are added independently, and scaling or multiplication with a scalar when all three coordinates are multiplied by the same number. Different geometries are embedded in this ambient space. For example, the two-dimensional Euclidean geometry is a plane in this three-dimensional ambient space defined by equation w is equal to 1. So it means that a point is a member of this geometry if its coordinates are x, y, where x and y can take an arbitrary value, but the third extra coordinate must be equal to 1. In order to describe spherical geometry, the spherical geometry is embedded into this ambient space as a unit sphere. The unit sphere is defined by this equation. This equation is nothing but the square of the distance of a point from the ambient origin. And this square of the distance is equal to 1. So indeed we have a unit sphere. Recall that in spherical geometry, instead of the sphere, we in fact have just a half sphere because points are diameters, or in other words, opposite points, also called antipodal points, are equivalent. Hyperbolic geometry can also be embedded in this three-dimensional ambient space as a one-sheet hyperboloid having the following equation. And finally, we can also embed the projective plane into this three-dimensional ambient world. The embedding is very similar to the embedding of the Euclidean geometry, but here, for the projective plane, we get rid of the extra dimension differently. Note that for Euclidean, spherical, and hyperbolic geometries, we reduce the dimension from 3 to 2 by imposing an additional equation that should be met for a point to be part of the geometry. In the case of the projective plane, however, we say that points of the projective geometry are in fact lines in the ambient space that go through the ambient origin. Or in other words, all points on these lines are equivalent. They are identifying the same point in projective geometry. There is one additional issue. Euclidean, spherical, and hyperbolic geometries are metric, so we have the notion of distance and angles. So we need the concept of scalar product in ambient space as well. This scalar product is the usual scalar product for Euclidean geometry and spherical geometry, but we will use a special scalar product for hyperbolic geometry, which means that the ambient space itself has an Euclidean structure for the Euclidean planar geometry and for the spherical geometry, but the ambient space follows the rules of Minkowski geometry here. The difference can be imagined by considering the theorem of Pythagoras as well. According to the theorem of Pythagoras, this is just the square of the distance from the ambient origin. In Minkowski geometry, the Pythagoras theorem is reformulated into the following form. So when we add the squares of the legs of a triangle, then when it comes to the extra coordinate, we have to use a negative sign. So interestingly, assuming Minkowski ambient space, this is also a sphere, because this says that the square distance from the ambient origin is constant for all points of the hyperbolic geometry. Let's focus on Euclidean planar geometry. We need a metric, so we need the magic wand behind distances and angles, which is nothing but the scalar product. The scalar product defined in the ambient space. So we use the Euclidean interpretation of the scalar product in the three-dimensional ambient space. Coordinates are multiplied together independently, and the three coordinate products are added. It is easy to see that such operation is commutative, distributive, and can be exchanged with a scalar multiplication. Euclidean geometry is embedded into the ambient space by requiring the extra coordinate w to be equal to 1. So points of the Euclidean geometry must have a coordinate triplet where the first two Cartesian coordinates are extended with a constant 1 value. You may ask why we do not embed the Euclidean plane with definition w equals to 0. Well, there are good reasons for that. One of the reasons is the following. We will want to express transformations, like for example translation or scaling by matrix multiplication. And it would be impossible for the translation if the ambient origin was also part of the Euclidean geometry. And it's easy to see why. If we have the ambient origin, its coordinates are all 0. If we multiply such a vector with a matrix, the result will be 0 no matter what the matrix is. On the other hand, translation must modify all points without exception. So the ambient origin cannot be part of the geometry because translation cannot be expressed for it as a matrix multiplication. So that's why we use the w equals 1 restriction instead. So these are the points in our geometry. What about the vectors? Vectors are directions between 2 points. A vector is not allowed to point out of the geometry. So from one point, the vector can point just into the direction of another point. We can also say that vectors are in fact the differences of 2 points. The constant 1 value in the extra coordinate would disappear, so we can conclude that valid vectors must have a 0 in the W position. Otherwise, the vector would point out of the geometry. So summarizing, in two-dimensional Euclidean geometry, a point is described by 3 numbers, and the third number is 1 for points and 0 for vectors. Let us examine the properties of vectors. A vector is just the separation of 2 points. If a point is considered as an ambient space vector, then the vector of our geometry is just the difference of these ambient space points. Vectors cannot point out of the Euclidean geometry, therefore their extra W coordinate is 0. It can also be seen by considering that the point's W coordinate is 1, so when we compute the difference of 2 points, the extra coordinate will be 0 in the result. The length of a vector can be computed by multiplying the vector with itself using the rules of the dot product and computing the square root of the result. Since in vectors the third component is 0, only the first 2 Cartesian coordinates show up in the length formula. This is nothing but the theorem of Pythagoras. From every non-zero vector, we can create a unit length vector, also called unit vector. The vector should be divided by its length. If we have a vector v, we can find vectors that are perpendicular to it. 2 vectors are perpendicular if their dot product is 0. Let us denote the components of the perpendicular vector by x perpendicular and y perpendicular, and using the formula of the dot product of the orthogonal vector and the original vector can be expressed in this way. So we can solve a linear equation for unknown coordinates x perpendicular and y perpendicular. And the solution of this linear equation is shown here. So if we have a vector with coordinates x, y, 0, then all other vectors that can be expressed in this form are perpendicular to it. And finally, we can recognize the parallel property as well by checking the coordinates. So 2 vectors are parallel if they have the same direction, but their lengths might be different. So one vector can be obtained from another vector by applying a scaling operation, and this scaling can be applied for the coordinates too. Okay, having points and vectors, the next step is the introduction of lines. A line is a constant speed motion in geometries, which can be expressed in this algebraic form, where p is the starting point of the motion and v is the velocity vector of the motion, or in other words, the direction of the motion. And we can imagine t as time. If we compute the time derivative of this motion, the derivative will be equal to v, so indeed we have a constant speed motion because v is a constant vector and is independent of t. If we compute the second derivative, which means the acceleration, the second derivative will always be 0. Recall how we defined the Gaussian curvature. First, we used the definition of the directional curvature, which is the curvature of a curve in a given direction. The curvature of a curve is just the centripetal acceleration assuming unit speed motion. In our case, the acceleration, including the centripetal acceleration, is constant 0 in an arbitrary direction. then the Gaussian curvature is just the product of the maximum and the minimum directional curvatures. However, in this case, all directional curvatures are zero, therefore the Gaussian curvature is also zero. So Euclidean geometry is a zero curvature geometry. The line can also be expressed with coordinates. So points have three coordinates that can be functions of time. And according to the definition of the constant speed motion, we separate it into the starting point, p, and a time-dependent term, which is just the velocity multiplied by the time. As the starting point is a point, the extra coordinate is 1, and as the velocity is a vector, its extra coordinate is 0. Note that this is the right way of assigning this extra coordinate, because in this way, for arbitrary t value, we get a 1 value in the result, so the result will always be a point in our Euclidean geometry. On the other hand, a vector is just the difference of 2 points. So let us select 2 points P and Q on our line and express V as the difference of the 2 points. Our line equation looks like this: P plus the velocity vector, which is now the difference of the 2 points multiplied by t, the time. This formula can be reorganized in the following way, which is called the combination of 2 points. By combination, we mean that we take points, multiply them with scalar values and add them up, and we expect the scalar values to result in 1 if they are added together. And this is exactly the case here, because 1 minus t plus t is always equal to 1. So the line is just a combination of 2 points, which can also be expressed with coordinates. Now both P and Q are points of Euclidean geometry, so their extra W coordinates must be 1. This is the right way, because if we look at this extra coordinate, 1 times 1 minus t plus 1 times t is equal to 1, so in the result the extra coordinate is 1. Points of the line are indeed points of our Euclidean geometry. Finally, we can give a third interpretation to the line using the external view of the ambient space. A line in Euclidean geometry is just the intersection of 2 planes in our three-dimensional ambient space. One plane is the geometry itself, defined with equation W is equal to 1, and the other plane is defined by 3 points, the ambient origin and P, Q, the 2 points identifying the line. This interpretation is important because this interpretation is valid not only in Euclidean geometry, but also in spherical and hyperbolic geometries as well. So when it comes to the definition of lines in hyperbolic geometry, for example, this is just the intersection of the hyperboloid and the plane defined by 2 points in the geometry and the ambient origin. This equation is called the parametric equation of the line because we have a scalar parameter which might be interpreted as the time. There is another way of expressing the points belonging to a line. We can use an implicit form which doesn't have any extra parameters. So far, we have defined the line as a constant speed motion. We also know that in the geometry we can find vectors that are perpendicular to a given vector. Now we find vector n that is perpendicular to the direction vector v of the line. This perpendicular vector is called the normal vector of the line. So the normal vector is perpendicular to v, which means that the dot product of the normal vector and the direction vector of the line must be equal to 0. V, the direction vector, is just the difference of an arbitrary point r on the line and the starting point of the line denoted by p. Having made this substitution, we arrive at an equation for unknown points r, which is called the implicit equation of the line. Indeed, if we have a point R, substituting into this equation we can determine whether this point R is on the line or not. This equation can also be expressed in coordinates, as n is a vector of our Euclidean geometry, its extra component is 0. R minus p is also a vector because both R and p are points, so in the vector the third coordinate is 0 again. And then we use the formula of the dot product, so the x coordinates are multiplied, the y coordinates are multiplied, and the two multiplications are added, and result in the well-known formula of the two-dimensional line. But we can also observe that the scalar parameters of x and y are nothing but the two Cartesian components of the normal vector. And the third component is just the dot product of the normal vector and p, the starting point of the motion, multiplied by -1. So a line can be identified by three parameters, the two components of the normal vector and this d. So this triplet is in fact the line. Ambient space points are also triplets because we need three coordinates to identify a point in ambient space. So we can say that lines with these three parameters are also members of our ambient space. So if we use this interpretation, the equation of a line is nothing but a scalar product, where we multiply the vectors of nx, ny, and d with x, y, and 1. So generally speaking, the line equation is just a dot product of the triplet of the line and the triplet of the point. And this dot product should be equal to 0 in order for the point to be on the line. Of course, we know that points are members of our Euclidean geometry if their W value is 1. This equation is an equation of the plane. In fact, the equation of this plane defined by the ambient origin and point P and vector V. So this interpretation means again that our line is just the intersection of two planes, the plane of the ambient origin P and V and the plane of the geometry identified by W equals 1. Finally, we call two lines identical if the same set of points belong to the two lines. Looking at the equation of the line, obviously the roots x-y pairs wouldn't change if we multiply both sides of this equation by an arbitrary number. So as a result, if we consider the line as a triplet of three parameters, the same line can be expressed in infinitely many different ways if all three parameters are multiplied by the same number. Two lines are equivalent if the triplet of one line can be obtained from the triplet of the other line by a scalar multiplication. After discussing two-dimensional planar geometry, let us consider the Euclidean geometry of the three-dimensional space. There will be no more figures after this point, because when we embed the three-dimensional Euclidean geometry into the four-dimensional ambient space, we lose the ability to depict geometric arrangements. But we can still use the correspondence or analogy between the two-dimensional planar geometry and the three-dimensional geometry of the space. So now the ambient space is four-dimensional. An ambient space vector is represented by four numbers. In the ambient space we still use the scalar product, where coordinates are multiplied together independently and the results of the multiplications are added. Recall that this dot product is responsible for introducing metric in our Euclidean geometry, including the determination of lengths and angles. So in this four-dimensional ambient space, points of the three-dimensional Euclidean geometry are described by four-element vectors where the force coordinate is equal to 1. Using the dot product, we can express the distance between 2 points as the length of the vector between the 2 points. The vector between the 2 points is obtained as a simple difference of the two four-element vectors. Similarly, we can introduce the notion of angle. Recall that the dot product is just the multiplication of the lengths of the two vectors multiplied by the cosine of their angle. So from this definition we can express the angle as the arc cosine of the dot product divided by the product of the two absolute values. In the ambient space, we have not only points, but also vectors. Vectors can be recognized by checking the force ambient coordinate, which must be equal to 0 in order for a vector not to point out of the Euclidean space. The computation of the length of a vector is based on the dot product, so we multiply the vector with itself and calculate the square root. As the force ambient coordinate of vectors is equal to 0, this W coordinate doesn't show up in the length formula, so we get back the well-known formula for the computation of the length of a three-dimensional vector. In three-dimensional Euclidean geometry, planes will be like lines in the two-dimensional Euclidean geometry. For example, the implicit equation of a plane is similar to the implicit equation of a line, but we have to use one more coordinate. You might think that we had too much mathematics, so let's jump into programming. What do we need from this theoretical stuff when we want to exploit Euclidean planes and Euclidean three-dimensional spaces in our computer programs? We will need primarily a structure or class called VEC4 or four-element vectors that can represent vectors in our ambient space, and as we have seen, these vectors can be points in the three-dimensional Euclidean geometry, also vectors in the three-dimensional geometry, not to mention planes in the three-dimensional geometry. So this VEC4 can define not only vectors but also points, planes, and we can even add colors, because we know that colors can be decomposed to red, green and blue components, and if we add the opacity as a fourth component, a color also needs four scalar values for its definition. So a VEC4 has four float variables x, y, z, w, and if we want VEC4 to represent a three-dimensional vector, then the w coordinate is set to 0. If it should represent a point, then the w coordinate is 1. If it is a plane, then the x, y, z components are just the coordinates of the normal vector of the plane, and the force w component is the d parameter of the plane that describes the offset of the plane from the origin of our ambient space using the units of the normal vector. So what can we do with VEC4 objects? We can construct it. This constructor just fills up the four components. An ambient space vector can be scaled by a number s when all components are multiplied. We can add two four-element vectors, which means that components are added independently. Similarly, we can subtract. Finally, if we had addition and subtraction, as an analogy, we can introduce an element-wise multiplication when x, y, z, and w are multiplied together independently. And the result is also a VEC4 type object. Note that addition and subtraction even show the type of the result. So, for example, when we add two vectors, so the w coordinates are 0. In the result, the w coordinate will also be 0, so the addition of two vectors is also a vector. When we add a point and a vector, which means the translation of the point by the vector, then the point's w coordinate is 1 and the vector's w coordinate is 0. So in the result we have a 1 value in the w coordinate, which means that the result is a point. Indeed, when we translate a point by a vector, we obtain a point. It makes sense to subtract one vector from another. When the w coordinates are 0, so is the w coordinate of the result, which means that the difference of two vectors is a vector. When we subtract a vector from a point, then we get a point as a result. And when we subtract one point from another point, both w coordinates are 1, the result will be 0, so the difference of 2 points is a vector. Concerning the element-wise multiplication, this operation doesn't make sense for vectors, points or planes, but it is really useful for colors, because when we know the own color of a surface and the color emitted by a light source, then the color reflected will be just the element-wise multiplication of the light source color and the surface color. Different wavelengths can be handled independently in color computation. We will learn why it has deep roots in physics. In addition to these basic operations, we will have the dot product, which is responsible for introducing lengths and angles. So the calculation of the dot product is just the multiplication of the coordinates independently and adding up the result. We can multiply two vectors when the w coordinates are 0, so this term doesn't affect the result. Or this dot product is also useful when we want to check whether a point is on the plane or not. In that case, A is the 4-element vector of the point, where the w coordinate is 1, and B is the 4-element vector representing the plane, where the w coordinate is just the d parameter, the offset from the origin. And if this dot product results in 0, then the point is on the plane. Otherwise, it is not on the plane. By checking the sign of the result, we can determine whether it is on one side of the plane or on the other side of the plane. For vectors, we can compute the length. The length is just the square root of the dot product of the vector with itself. A vector can be normalized, which means that we find a vector that points into the same direction but has unit length. So normalization means a scaling with the length of the vector. And finally, we can combine 2 points. It is also called linear interpolation. So P and Q are points and T is a scalar parameter. If T runs in the unit interval between 0 and 1, with this formula we can generate points on the line segment defined by P and Q. Or if T can take an arbitrary value, then this formula generates points on the line defined by points P and Q. The VEC4 class and these additional global functions are just the summary of the mathematical knowledge of Euclidean geometry when it is embedded in a 4-dimensional ambient space. Well, sometimes we decide not to represent this extra w coordinate explicitly because we know whether an object is a vector or a point, but of course we will not be able to represent planes or 4-element colors, including the opacity as well. But we save some memory. So VEC3 is a simplification of the VEC4 structure introduced earlier. It can also be constructed. We can scale a vector. We can add 2 vectors, even 2 colors, or we can add the point and the vector. And similarly, we can subtract 2 vectors, we can subtract 2 points, we can subtract a vector from a point. The difference between this VEC3 and the previously introduced VEC4 is that we will not be able to detect the type of the result by checking the w coordinate. If we have VEC3, then the dot product is able to compute the dot product of two vectors, but obviously this function is not appropriate for determining whether a point is on the plane or not. We have not only the dot product, but also the cross product in the three-dimensional space, which can be evaluated by this formula. That concludes our chapter on analytic Euclidean geometry. So let me summarize the most important messages. We have to use an analytic approach to geometry because the computer cannot do anything else but to deal with numbers. Expressing geometric concepts with numbers means that we have to use coordinates in a coordinate system. It might be surprising, but we took an external view, which means that when we have a space, either two-dimensional or three-dimensional, we embedded this space into a higher dimensional space, and we call this higher dimensional space as the ambient space. So the ambient space is three-dimensional when we deal with two-dimensional Euclidean geometry, and the ambient space is four-dimensional when we consider three-dimensional Euclidean geometry. This gives us an extra coordinate, W, and this extra coordinate for Euclidean geometry and for points is equal to 1, and for vectors it's equal to 0. This strategy can also be applied for non-Euclidean geometries, like spherical, hyperbolic, or projective geometries. But in those cases, points, vectors are represented differently as elements of the ambient space. In metric geometries, like the Euclidean geometry, we need the definition of the dot product because both the length and the angle are derived from the dot product. The line was introduced as a constant speed motion. The line is also the shortest path, also called geodesic, between 2 points. And this is true for any geometries, not only for Euclidean geometry. Finally, we have seen that on the programming level, we need just a class or structure called VEC3 that is able to store 4 float values representing the 4 coordinates of the ambient space. Sometimes we get rid of the extra coordinates, so this VEC4 can be VEC3 and even VEC2 if we handle the missing coordinates implicitly. So this really concludes this chapter. Thanks for your attention.